you ready?
Yeah.
Okay. Tamanna is going to give her second talk. So, thanks.
Okay, so let me first share the screen properly. So let's first recall some stuff from the previous talk, and then I'll give a short overview like before, and then we will jump into the talk. So last time we first talked about, like, we started with a group that was complex, connected, reductive algebraic group, and then we fixed a cocharacter map, which gave us the grading on the Lie algebra, and also a group G0 that was the centralizer of the image, and we got that G0 acts on Gn, and I said that we are interested in the G0 equivariant bounded derived category on the graded piece, and for n not equal to 0. And then we talked about the bounded derived category. So derived category, both equivariant and non-equivariant. So non and equivariant. Sorry, I don't know, like, okay, sorry.
Can I ask a question?
Yeah,
Why do we, never mind, I think I answered my question.
you're asking why and not equal to 0.
Yeah.
Yeah. Okay, so yeah, only for n not equal to 0 we get finitely many orbits, G0 orbits. That's important for certification. So yeah, so we denoted it by this. And then we talked about the perverse sheaf, which is a abelian category, both in the equivariant setting and non-equivariant setting. So I'm just writing the non-equivariant one. And then we talked about the simple elements in the simple objects in the in this category. And we saw that for nilpotent cone and for GN, for the graded setup, they are actually have a similar kind of correspondence with the pairs. For example, for nilpotent cone, this is the G nilpotent orbit, and this is the local system, irreducible local system on C, and we have the same kind of correspondence for GN also. And then we talked about, let me change the setting. Yeah, then we talked about parity sheaves, and I said that to talk about parity sheaves, we need some parity vanishing condition, or the homology vanishing condition, that I will again come back in this talk. So I probably did not mention in my previous talk that in characteristic 0, parity sheaf coincide with ICs. So the IC associated to a pair is same as the parity associated to that same pair in characteristic 0, but in positive characteristic, they are new. They are new objects. Okay. And this I mentioned before, that Yeah, so what I'm forgetting something to mention. Yeah, I don't know. I cannot remember what I wanted to mention here. Anyway, okay, let's move to the next part. I don't think it's very important, or I will remember it in between. Okay, so now I will go to the overview. So what I'm going to do today. So today, the main aim is to talk about Lusztig's results first in characteristic 0, and then we want to talk about how to extend it in positive characteristics. So remember, like this box. So here I have 0 characteristic. This is the greater than 0 characteristic. So Lusztig result is here, and my result will be here. So to talk about Lusztig result, before I will define two functors, restriction. I will also define it in the graded setup. So when I'm writing the capital G and P, it's on the nilpotent cone. I will also define it on the graded setup. There I will use the small G and P. The next Lusztig result. The rest of the talk will be how to extend. And under that, I will talk about some assumption that we need. We need some conjectures. One of them is Mautner's cleanness conjecture. Then I'm going to talk about the results that I proved in my paper. I'm going to give an example of one of the conjecture. Like one is made by Mautner, and there are some like examples. Those are like well-known examples. And one conjecture that we made in this paper, and I'm currently working on one of these conjectures. So I'm going to give some example where we calculated it. Last, if possible, some future direction probably. So that's how it's going to be. So now let's go into the talk. So I'm going to define induction and restriction on the nilpotent cone. So for that, I fix a parabolic containing a levy, and I need a diagram like this. These are the nilpotent cones on the levy and the parabolic. So this is the projection map. This is the inclusion map. This map sends Gx to Gx. Okay. So what induction and restriction does? Like induction is a functor from L equivariant bounded derived category on the nilpotent cone of the levy to the G equivariant bounded derived category on the nilpotent cone of original group, and the restriction is in the opposite direction. So before going into the formal definition, what it actually does, like these two functors, like it allows me to go from the bigger group to the smaller levy, or from the smaller group to the bigger, the original group. So it allows me to like go from smaller to bigger, bigger to smaller. Okay. So if you so the formal definition I'm giving, but like if you don't know what these maps means, you don't have to care. Like you just know, like it's like gives me the freedom to move from smaller to bigger or bigger to smaller. So induction is we first pull back from here from NL. Then I apply the, this is called induction equivalence. So I apply the induction equivalence. I apply the inverse of the induction equivalence. It's a equivalence, so I can take the inverse, and then then I push forward by the mu map. The restriction is defined on the other way. So for that, actually, I need an inclusion map. Let's call it I, inclusion of NP in energy. So I first actually forget the G equivariant structure and then pull back and then push forward. Okay, so if you don't know what this map means, then you don't have to care about it. It just allows us to go from small to big, big to small. So a remark is that this restriction is left adjoint to the induction. Okay, so these are whatever I defined, it's on nilpotent cone, and whatever I'm defining on nilpotent cone, I'm going to define it in the gradient setting also. Okay, so let's go into this now. So this is like, here I will talk about cuspidal pairs, and these are some very important pairs that we will deal with. So before that, I'm using a notation from now just to write it easily. So this set is the collection of the pairs C and F, where C is G orbit in the nilpotent cone, and F is a local system, G equivalent local system on C. Okay. So a cuspidal pair, CF in IG is cuspidal if for any proper parabolic P, I have this condition, restriction GP of the IC associated to this pair to be 0. Okay, so yeah, so I can, yeah, so I can actually define it in a different way also using the adjointness. So here I'm saying that if I pick any parabolic, the restriction is 0. I can say it in other words. ICCF is not being induced from I don't know what's happening. Induced from a pair on a smaller levy. Levy. What does it mean? That there does not exist any levy L and any pair, let's say CLEL on this set, so that induction of, let's say this L is contained in a IC CLEL will give me back this IC of CF. Okay. So I can use both the definition, and you can see like it can be proved very easily by the adjointness of the restriction, like left adjoint to the induction. Okay, so yeah, so that's the definition of cuspidal. And I will probably sometimes use this notation for the cuspidal pair, collection of cuspidal pair on G. So in Springer theory, what we do is that in Springer theory, we study how to get ICs from induced cuspidals. And that is something similar we are going to do here on the graded setting. So now I'm going to define induction and restriction on the graded setting. Okay, and I'm going to use the same kind of diagram, but in the with graded pieces. So let me first show you the similar diagram, and then I will say something about it. So this is the diagram I want to use, and just to make sense, the diagram should make sense. I need some condition on the parabolic and the levy. So I need this image of chi to be contained in my levy and the parabolic. Okay? Just so that the grading makes sense. So this is the diagram, and actually all the maps are same. The way I define the maps in non-graded setup, it's the same map. So I'm not defining it again. Let me just tell you now, this induction is from the L0 equivariant on the graded piece of levy to G0 equivariant on Gn, and the restriction is on the other way. Okay. So the definition is same and the remark is also same. So restriction again, left adjoint to induction. Okay, so now I'm going to define cuspidal on Gn now. Previously I defined on nilpotent cone. So cuspidal on Gn. Oh, so before that I will again. I don't know, like why, like it did not happen last time. Sorry. Okay, so again, like IGN, this is the collection of pairs OL, where O is now G0 orbit on Gn or in Gn, and L is a local system on O. So here a cuspidal pair OL is cuspidal. Does anyone have any solution to this? What's wrong I'm doing so that it's going back then?
You got an update and it started using all gestures to change apps.
So what should I do then? That's that's hard. Okay. Okay, so this is cuspidal. If there exists a cuspidal pair in the bigger levy on the nilpotent setting, so that C intersection GN is O and L is actually coming from the restriction of F on O. Okay, so a pair in the graded setting is cuspidal if there exists a cuspidal in the nilpotent setting whose restriction is this pair. So you can ask me if it still satisfies this condition. Right, because that was the definition for, that was the definition for cuspidal in the nilpotent setting. So if this is true in this setting, the way I defined cuspidal, and I don't know, like, so this one actually, Lusztig has proved, Lusztig proved a similar result, but that's not exactly result in characteristic 0, which is not exactly the restriction functor, but it's like probably we can do some modification and make it a restriction function and prove that it is true for characteristic 0, but I still don't know like if it can be proved in characteristic positive. So don't know for positive characteristic. Okay, so yeah, so that's how we define cuspidal on GN, and it's quite different from the nilpotent setting. So now I move into the results of Lusztig, that is in graded setting, but in characteristic 0. So okay, so this theorem says that for any pair OL from the graded piece, there exists a parabolic P with a levy L and OL EL in the cuspidal, like it's a cuspidal pair in the levy, graded piece of the levy, such that ICOL appears as direct summand of induction of this cuspidal pair. Okay, so I take a pair in the bigger group, in the graded piece of the bigger group, I can get a cuspidal pair on the smaller levy, so that this one I pick is being induced from that cuspidal pair on the smaller levy. Okay, and this is not true in positive characteristic. And one of the reason is that the decomposition theorem is not true in positive characteristic. So now following the other results, of modular representation theory following other results in modular rep theory. One guess was that we can replace this theorem by something similar associated with the parity sheaves. With parity sheaves. Okay, so that's why we think about parity sheaves now. So when I want to extend it in the positive characteristic and I know like it's not working for IC, I need parity sheaves, then I need something more, because to talk about parity sheaves, my environment becomes more restrictive. I need the cohomology vanishing condition. Also, I need the existence, because we don't know if the parity sheaf exists. So we need many things. So first I will move into the assumptions on the field. So now my field K is a positive characteristic field, and I need two more assumptions on it. One is that K is big enough for G. I'm not going to give the exact definition. I can tell you vaguely why I need it. Like, I still want to use the result from the characteristic 0. So I need something like tensor product kind of thing from a characteristic 0 field to my positive characteristic field. So also I need, when I will do that tensor product, my irreducible local system still needs to be reducible there. So big enough is something, that kind of condition that allows me to like extend the irreducible local system to a irreducible one in the positive characteristic field. Okay, so that's a very vague definition probably. Yeah, so the next one is that I need characteristic of K to be is pretty good for G. So what does this means? If I take for any x in the nilpotent cone of G, let's say this one is characteristic K is P. Okay, so I want this P. P is not torsion prime of this group. So if I take G, like if I take the centralizer of X in G, if I take the identity component of that, and then if I take the reductive quotient, I don't want P to be the torsion prime of this, which means again, like let's say this is the H group, this is H, then I don't want this H to have, like the fundamental group of H to have no P torsion. No P torsion. So it's, this one is also very, not very restrictive. Like I think for most of the classical groups, you just have to remove 2, otherwise it will be fine. Yeah.
Type A.
What?
Type A. I don't think you don't want to divide in type A.
Yeah, for type A, I think, yeah, not to divide it. Yeah. For C and D, I think 2 is only the problem.
So you're looking at the weight laws. Right. You want to make sure that two is divided.
Yeah. So these are the condition I need. And then remember that I talked about the homology vanishing condition, and that's essential to talk about parity sheaves. And I have told you last time what does it mean for nilpotent cone, and that's the same statement I am writing it. Actually, this one is proved by Jutta, Mautner, and Williamson in their paper Parity Sheaves. This is not exactly this theorem, but we can rephrase this theorem using our assumptions. So this theorem says that for any G orbit in the nilpotent cone and any local system F on C, I have G equivariant cohomology of F to be 0 for odd degree. Okay. So I needed something like this in my setup, that is the graded setup. So the theorem I proved is that for any G0 orbit O in Gn and any local system L in the G0 equivariant setup on O, I have G0 equivariant cohomology of L to be 0 for odds. Okay, and this is one of the theorem where I really needed that pretty good condition. Yeah. So once I have this theorem, now we can talk about parity sheaves. It's still not assured that the existence, but we can talk about parity sheaves in the graded setup. Okay. So now I'm going to talk about Mautner cleanness conjecture. So before that, I should mention what clean is. So a pair, let me use CN. A pair CF from IG is clean if F has vanishing stock on C bar minus C. Okay. Okay, so this is the definition of clean, and then the conjecture that Mautner made was that if characteristic of the field is pretty good, then any cuspidal pair in IG is clean. Okay. So this is already have been proved for some cases. So already proved for when the characteristic, this is P. So if P does not divide the order of the well group, then it is true. B is that if G, for the group G, the irreducible factors of the root system are of type A, B4, C3, and D5, and also of exceptional type, then also it is true. Okay, so it has been proved. And still unknown for general case. So now I define cleanness on my graded piece, and here the definition is quite similar. So I pick OL from IGN, it's clean if L has vanishing stock, on the complement of O in the closure. Okay, so this is quite similar to the cleanness definition of cleanness on the nilpotent setup. So now I will talk about the existence of parity sheaf on cuspidal pair. Okay, so now I'm here, GN and positive characteristic. So now I'm in the positive characteristic. Okay, so this is a new result. So theorem, it says that for any cuspidal OL in IGN, ICOL is clean. Okay, so for any cuspidal, the associated IC is clean, and the immediate corollary I get from this, so once it is clean, this IC of OL is actually pushed forward of the local system with some shift. And I can combine this with the cohomology vanishing condition, which says that this is 0 for odds. So these two facts ends up in this corollary that for any cuspidal, ICOL is same as the parity of OL. And I know IC exists, so EOL exists. Okay, so existence of parity for cuspidal is proved. Okay, so now I need to make another conjecture. This is the conjecture 2, and this one I want to give an example at the end. So this says that for any, what's that? Okay, so for any parabolic P with a levy L and any cuspidal, let's say CL, EL in the levy, the induction of the IC is parity. So this conjecture lies on the nilpotent cone, but in characteristic positive. Okay, so this one is true in characteristic 0, still unknown in positive characteristic, so in my next paper, I'm working on this conjecture, trying to prove for classical groups. And I have actually calculated 2 examples in my current paper where it is true. Samples with SL4 and SP4, and one of them I will probably show you at the end of this talk. Okay, so here it has been already shown that it is true. Okay, so with this assumption that these 2 conjectures are true, now I go into the results. So the first result is the replacement of Lusztig theorem from characteristic 0, and it's quite similar. So for any pair OL in the graded piece, there exists a parabolic with the levy and the cuspidal pair, cuspidal, let's say OL, EL in the levy, such that now my parity sheaf associated to the pair appears as direct summand of induction of the parity sheaf associated to OL, EL. Okay, so you can see this is the exactly same kind of theorem that's proved by Lusztig, but ICs got replaced by the parity sheaves. Okay, so the next result that kind of follows from this theorem is that now for any pair OL in the graded piece, EOL exists. So now the existence is proved for any pair. Previously we proved it for cuspidal pair. Now the next theorem is that for any parabolic P induction GP sends parity to parity. Okay, so these are the results from my paper. Now I'm going to go into the conjecture 2 again, and I said that I'm going to give an example. So here I'm going to give an example of the conjecture 2. So remember that it says that if I pick any parabolic with a levy, and if I pick a cuspidal pair, let's say CF in the levy, induction IC of CF should be parity. This is I need. Okay, so I pick a group G SL4. So let's see what are the levies. So the levies are Okay, here I'm using a notation S of GLM, GLN. It suddenly became so sensitive, this iPad. Wherever I'm touching, like something is coming. Yeah, okay, so this is the like this kind of matrices. This is M cross M and N cross N, where I have date A and date B. That's equal to 1. Okay, so the the Levy subgroups are GL1 cross GL3, then S of GL2 cross GL2, S of GL2 cross GL1 square, and the torus. Okay, so I want to show that for any Levy and any cuspidal, this induction is valid. But unfortunately or fortunately, like this one only have cuspidal pair. On other levies does not have. Torus actually, like it's the Springer theory, so I'm not going to show it for torus. So I'm just interested in this one. Okay, so I pick that levy, and then I have so the cuspidal pair on this levy is this one. So this is the principal SL2 orbit. And this one actually the non-trivial local system on O-ring. Okay, so this is the Levy subgroup. Sorry, this is the cuspidal pair. So just to make it easy, like let me write this to be O, this whole thing to be O, and this to be E. Okay, so I want to calculate int GP of this ICE OE. I want to actually know what the stocks are. So if I pick any X from the nilpotent cone, then how the stocks behave, right? So now remember the diagram, the induction diagram. I'm using a modified diagram here. So I can use this induction diagram, O plus UP going to G cross P, O plus UP, that's going to NG. And so I go here by induction, then I take the stock, that means I restrict it to X. Instead of doing that, I can actually do a base change and do this thing, like I restrict it here, like go up to here, then restrict it here, and then push forward by this constant map, which means like taking the global section. Okay, so I end up here. Okay, so if I start from here, let's say this is my E. I start from here, I pull back here. So pulling back means I still have a local system. Here I have the induction equivalence, so I still have a local system. Here also, when I arrive here, I have a local system. And then the local system I have here, let's say F, I actually want to calculate the global section of that F, right? So that's where my problem reduced to. or which is same as this. So I start with the x. Now I want to start with like x from each orbit of the nilpotent cone. Okay, so the orbits in the nilpotent cone are O4, O31, O2 square, O2 1 square, and the t. So I pick x from each of them, and I want to see how, let me change the color. Okay, how this space looks like. So my problem reduces to how this space looks like. Okay, and for O4, this is just a point. Sorry, it's just a point. For this one, it's P1 minus 2 points. For this one, it's A2 union A1. This one 5, this one 5. Okay, so you can see x. Yeah, sorry. Yeah, the intercept. Yeah. Yeah, so except this one, all of them like it's simply connected, right? So the local system on a simply connected space is just a constant sheaf. So except this one, my problem reduces to calculating the cohomology of the space. Okay, so I just need to know how this space, like what's the cohomology of this space, except that one. For this one, the calculation is a little bit different and complicated, but the good news is that I still end up something that has 0 in all the ranks, or in all the dimensions. So what I get finally is this, like in -8, I get something non-zero here. At -10, I get something non-zero here. Sorry, not here. I get 0 there. So here, and in -14, I get something non-zero here. So you can see the non-zero things only appears in the even degree. Okay, there's no other non-zero stuff. So that proves that induction of that IC that we picked. Yeah, that is valid. So that's the concept that we use to prove it in classical groups. So yeah, so that's the next project we are trying. Yeah, so that's all about the talk. So for the future direction, like, yeah, I'm still trying to prove it, the conjecture 2. And once we are done with the conjecture 2, we can actually extend it more. Like, so for the conjecture 2, we did it for cuspidal pair, like we want to show the induction of cuspidal is parity. Then we can probably try induction of any pair is parity. It's actually a part of unpublished conjectures of Mautner. So this can be, I think, probably a decent project. And also, like, I haven't thought about all these things much, but like there's some, like, the way Lusztig worked in Z grading, the similar kind of work Lusztig and Yoon has done, which is much more complicated. Sorry. Yeah, Yoon in Z mod M grading, where like instead of like induction, they have E-spiral induction, and things are more complicated. And they again have worked in characteristic 0. So one direction can be like extending that to characteristic positive. tending to positive characteristic. The third thing can be like, so we prove that for any pair there exists a cuspidal. So existence of cuspidal is proved. Existence of cuspidal proved, but I don't know about the uniqueness. What about uniqueness? Yeah, so I don't know much about any of this, but these can be like some future directions. Okay, so I will stop here.
I had a question.
Yeah.
So on the previous slide, did you need to take the compactly supported cohomology because those spaces are not compact?
Yes, yeah, actually we are doing complex.
It wouldn't just be the global sections, it would be some kind of compactly supported thing, would it not? Or am I missing something? Because the bottom map there is not a proper map.
Which map you were
The
saying?
very bottom map there on the right, that map is not proper, right? Because those fibers are they're not compact. And so do you need to take the compactly, when you push it forward, do you need to take like the shriek push forward or something like that? Like then do you need to?
So the definition of induction is like the shriek push forward. So when we are here, like I think we're still doing the shriek push forward, right?
So basically, so I guess what I'm asking is, so when you're doing this cohomology, these local systems on those spaces, do you really need like the compactly supported cohomology? Because wouldn't that be the shriek push forward? I mean, I'm not really an expert on it, but.
Yeah, but I don't think like I cannot probably give you the answer, but I don't think I took the compactly supported cohomology. But yeah, now I'm also confused like why I did not do that compactly supported cohomology because what? Clean. Oh, you mean like for clean? No, I don't think that's like clean is here, but I don't know like what's happening in between, right? So like the compactly supported cohomology, like that things come here when I'm pushing forward. So I don't know what happened to that clean local system in the intermediate steps. So that's not associated to the fact cleanness, I guess. Yeah.
Follow the green arrows, or you just get derived under the global sections of the global system?
Are you saying about this?
Like going from epsilon to yeah.
I'm just like this one, just like pulling back, right? So it's not the like.
It might actually be related to the cleanness fact, because if you wanted to do this for a general induction, not necessarily a cuspidal, then you would have to take the orbit closure, and then that mu is a proper map. And so the two push forwards are the same. But since you're
Oh,
to replace it with
yeah,
just the
right.
orbit,
Mu is proper.
well, if I put the orbit closure there, it's proper.
So you're saying because it's clean, you can put the orbit closure and it doesn't change it somehow? Is that the issue? Is that the point of cleanness?
Yeah, like if it's not clean, then I cannot use this diagram.
Yeah.
I can only use this diagram because it's clean. Yeah, so I think it has something to do with the cleanness. Yeah. So this modified, like when I define induction, I actually didn't use this diagram. This diagram only we can use when I have a clean local system or the cuspidal.
Okay, thanks. Thank you.
Yeah.
So is this the essential place where cleanness is important? I mean, that I've never really understood why cleanness is important, but is this sort of why cleanness is important?
Yeah, like in the paper also, like for some proof, I really needed to use this diagram. So like this diagram only can be used when it's cuspidal or clean. Otherwise, like I don't know, like what's the importance of the cuspidal pairs. Yeah. Do you have any answer, Laura?
I don't know, it's a little mysterious.
Yeah.
And I feel like all of it's kind of circular, so it's not really the essence of which aspect is like the important thing. I think the important thing is that these are like sort of the cuspidal pieces that can't be built up from the smaller bodies.
Yeah.
And it's somehow intrinsically linked to the fact that it's clean. But we don't have a good understanding of why that's true. In fact, for the nilpotent cone case, Lusztig proves this fact just case by case, like for each of the types.
Yeah.
And so we don't have what's the word when you just like have an intuitive knowing of why something's true? Like we don't have
There's no uniform proof.
there's not a uniform proof, so we don't have a good intuition for that relationship, I think. Which probably we did be better at being able to handle better Mautner's conjecture.
Yeah.
Positive characteristics.
So in the modular representation theory, like the generalized modular Springer theory, like their cuspidal pairs play the important role to define the perverse sheaf on the nilpotent cone, like define it as the disjoint union of this induction series, I guess. So yeah, so there I think like their cuspidal has an important role, right? Yeah, I don't know, like if there's something similar here, like
I think there is.
yeah,
I mean, I think it is exactly similar.
it's the same kind of theorem we are proving on the graded setting, right? Like
It's more complicated.
yeah, yeah.
Can I ask something really quick about your last slide?
Yeah.
That, I was wondering if anything is known for, so you were talking about one of the generalized to different gradings. But like other things known for like maybe specific gradings, like if they want to very small things.
Yeah, so for like whenever like you go into the mod M or the mod 2, I think like you cannot really work with this general induction and restriction diagrams. You will have to play with the spiral induction and restriction, and that's quite complicated, quite different from this definition. Yeah.
Other questions?